All right, taking a look at the key for quiz number 4. For this problem, I wanted to give a possible aldehyde Grignard reagent for the product below. There's actually 2 options you could do this. We had to recognize what you'd had to break a bond, or make a bond, one of 2 ways between carbon 1 and 2, or you can make a bond between 2 and 3. So if I did the 2 and 3, that would be these 2 in green. You can see how it's numbered, so that the carbon 2 would have the aldehyde piece, and carbon 3 would be the Grignard. And the biggest thing here was to not lose other pieces. The blue version, shown down below, equally as good. And the blue version, the aldehyde's on this side, so you can see this alkene over here, and the Grignard would be at carbon 1 instead of carbon 3. 2 points for the Grignard, 1 point for the aldehyde. So number 2, I want to make sure you added all lone pairs and formal charges to reagents and molecules below. So you had to put a negative charge on your aluminum, plus charge on your lithium, and add, of course, lone pairs to everything where you need to be. The second part was to give a mechanism for the formation of the product alcohol given. And then finally we asked for the other alcohol. So lithium aluminum hydride essentially can react as just 4 H minuses. So that's what I did here. You do step 1, you do the addition, make a tetrahedral intermediate. Do we have a good leaving group? We do. So we kick out this piece here. That stays there. That's fine. Let's let it sit. We've made an aldehyde now, which is actually more reactive than this ester. So another H minus, right? Remember, we have 4 of these because there's 1, 2, 3, 4 of those. Another H minus comes in, does an addition, adds in, breaks the pi bond, make another tetrahedral intermediate. This tetrahedral intermediate, however, has no good leaving groups. So we go on to step 2, which is just protonation. So we make sure we start our arrows at electron density. So a lot of folks trying to protonate, the arrows going the opposite way. Be careful with that. So that's a protonation step. And that gives us the other alcohol we're forming. The final product, lone pairs of charges is 1, 2 for each arrow, 2 for arrows, 2 for arrows, and then 1 for the double protonation. So this one, give a complete mechanism with arrows and molecules in each of the boxes below. First step was to form this Grignard. That's that radical process. So you show these fish hook single-headed arrows. That gets you to this Grignard. So the arrows were +1. Drawing this Grignard molecule was +1. This Grignard then reacts with the less substituted carbon because this is considered basic conditions because the Grignard has a negative charge, carbanion, so it reacts with the less substituted carbon. Make sure whatever carbon you react with, that's the bond you break in the ring. So you get +2 for the arrows, +1 for the regio selectivity, having your Grignard react with carbon 2 and not carbon 3. Once you make the Grignard, you get this intermediate here. It's like a tetrahedral intermediate. There's no good leaving group, so the final step is a protonation. So 1 point for the protonation, and then +1 for the final product, with the alcohol being on carbon 3, according to my numbering. Final question. First thing I want to do is circle the kinetic product. So then the kinetic product comes to the most stable intermediate. This would come from the most stable intermediate because it would come from a tertiary carbocation. This is the thermodynamic product because it has a more substituted alkene, 1, 2, 3, versus the 1, 2. So this is the more stable product. This comes from the most stable intermediate, so this would be considered the kinetic product. So the first step, so you circle that, so with +1. The first step then would be give the mechanism. So the first step is going to be protonation. We protonate, that's +2. Leaving group leaves, the water leaves. We do a hydride shift, because this is a secondary carbocation. If we do a hydride shift, we get a secondary allylic carbocation. So it's more stable. So +1 for the rearrangement, +1 for the substitution, gets us the thermodynamic product. Key here was to recognize you do this rearrangement. A lot of people lost or tried to number things differently, but a secondary carbocation is less stable than a secondary allylic carbocation. That's the key to remember. And then also the intermediates, make sure the intermediate was the kinetic. The kinetic one comes from the most stable intermediate. In this case, the tertiary allylic carbocation, which would be a resonance form of this one, shown here. And of course, you get +1 for the kinetic product. That's it.